Hello, it's time for another slice of physics. We have been talking a lot about magnetic force from an external magnetic field on a moving charge, and now we're going to tackle a magnetic force on a current. Since a current is nothing but a lot of charges moving in the same direction, it follows from the force on a moving charge that there probably should be a force on a current as well. And that's what we're going to look at. We're going to understand its magnitude and its direction. Okay, in this example, I'm going to take an external magnetic field that is coming out of the screen. So it looks like this. And I'm going to take a current carrying wire that lies horizontal, although I've struggled to make this line completely horizontal, just pretend that it is. And there is a current going through that wire. So there's a current in the wire, there is an external magnetic field, and there is a length, and this length L is not the length of the wire, but it's the length of the overlap between the wire and the external magnetic field. So it's the length of the segment of the wire where the external magnetic field exists. So we have an equation for the magnitude of the force. The force on the wire from the external magnetic field is given as I times L times B times sine of alpha, where alpha again is the angle this time between the external magnetic field B and the current I. So instead of the direction of the motion of the charge, we have the direction of the current. And it depends on the length, which is the length of the overlap between the magnetic field and the current itself. So the stronger the current is, the stronger the force is going to be. The more overlap length we have between the current and the magnetic field, the stronger the force is going to be, and stronger the external magnetic field is, the stronger the force is going to be. Let me try to change colors of this wire. It's going to be tricky to draw right on top of it, but hopefully you can follow this. And I'm doing this for a reason. So let's say the wire is green, and so I'm going to use the magnetic field of the current. So since we have talked about each current having a magnetic field, you might be getting confused between the external magnetic field and the magnetic field of this current. So that's why I've changed colors here to show you the magnetic field from this current. So in order to get the magnetic field from the current, we go back to the first right-hand rule. We've been playing with the second right-hand rule for a while, but now let's go back to the first right-hand rule. And so I grab the wire, I put my thumb in the direction of the current, and my fingers are curling like that. So the magnetic field is going to be like this. So which means above the wire, the magnetic field will be dots. I'm going to show them as smaller dots just to distinguish it from the external magnetic field. And below the wire, it's going to be X's. So I don't want you to confuse the magnetic field of the current from the external magnetic field. The magnetic field of the current itself will not apply a force on the current. That would not make sense. It would be like pushing a car from being inside the car. But the external magnetic field, whatever caused it, in this case it could be a set of magnets, it could be a set of other wires, we don't care what caused it, but the external magnetic field does apply a force on the current. So that's the magnitude. And once again, let's just take a quick look at the units here. So I've got Newton as the unit of force. I've got amperes as the unit of current, meters as the unit of length, and Tesla as the unit of magnetic field. Sine alpha has no units. So rearranging this, I get Tesla equals Newton over ampere meter. That becomes kilogram meter per second squared divided by ampere meter. Ampere is nothing but Coulomb over second. So that becomes, second comes to the top and Coulomb remains in the bottom. And now I can cancel the meters, I can cancel one of the seconds, and we get the same answer as before, kilogram over Coulomb second. So this equation works out from a unit standpoint as well. And once again, we confirm that Tesla is kilogram per Coulomb second. All right, let's talk about the direction of this force. So in order to do the direction of the force, I have to use the second right-hand rule. And as I use the second right-hand rule, it's the same as before. The only additional condition we have here is that we take the direction of I, current, as the direction of motion of positive charges. Since current model is flow of positive charges, That works out well. It's consistent with the model or the definition of current. And so we use the second right-hand rule in that fashion. So in this case, I will have my thumb pointing to the right in the direction of current. I will have my fingers pointing out of the page to be consistent with the direction of the external magnetic field. So thumb is in the direction of current. Fingers are in the direction of the external magnetic field. And then the palm, when you hold your hand like this, you'll see that your palm is facing down. The direction of the palm facing gives you the direction of force. So this external magnetic field on this wire will have a force that's acting down like this. It'll be acting all along this wire over the region where the magnetic field and the wire overlap. So we have the magnitude and we have the direction. And by the way, just a quick note here, you can think of this force as an interaction between the magnetic field of the current in the wire and the external magnetic field. That is in fact what happens because the current has its own magnetic field. That magnetic field interacts with the external magnetic field, and that's why you have a force. And so below the wire, you see that the magnetic field of the wire and the external magnetic field are opposite. So you might think that they would attract. Above the wire, they're the same, so you might think that they will repel, which kind of explains the direction of this force. But the more reliable way to get the direction of the force in all these cases is to use the second right-hand rule and just use the current model where you pretend that the current is the flow of positive charges. So because we have a positive charge always here, we don't need to worry about any reversal. So no reversal to worry about because current is the flow of positive charges. All right, that'll do it for this video. So we have looked at the magnetic force on a current carrying wire from an external magnetic field, and we saw that it depends on the current, the external magnetic field, and the overlapping length, and I should also add here, and the angle between I and B, which in a lot of cases will be 90 degrees, so it tends to go away. And the direction of this force is determined using the second right-hand rule, where we treat the current as a moving positive charge. So no worry about reversing the direction once we find the answer. There are many useful applications of this. One of the most common ones is electric motors that every one of us uses every day, and we will be talking about that in a future video. Thank you.